Welcome to Lagrangian online classes. I'll be taking the subject Power System Analysis, EE306, Module 5, Economic Dispatch and Unit Commitment. I'm Santhi, Assistant Professor, Department of Electrical and Electronics Engineering, Rajgiri School of Engineering and Technology. So we are moving to the session overview. I'll be what we'll be seeing in this session. We'll be introducing to the topic on economic dispatch. Next we'll be seeing what is the input-output curve relation in a generating unit. And next we'll be seeing what is the incremental cost curve. Then economic division of plant load between the generating unit within a plant. And we'll be seeing what is transmission losses and loss coefficient. And then we'll be moving on to what is the economic division of system load between different plants in a power system. Yeah. So the introduction. So we know that in a power system network we have got several power plants. Each power plant, it has got several generating units within the plant. Now at any point of time we have to see that the system load has to be met by the different generating units that is operating within the power system plants. So what is economic dispatch problem? The economic dispatch problem or the control, it determines what should be the power output of each and every plant of the generating units within a plant, and with the main objective of minimizing the overall cost of fuel that is needed to serve the system load. So this is what is the economic dispatch problem. So it is nothing but you have to distribute the load among the different generating units within a plant so as to minimize the overall cost of fuel needed to serve the system load. So how will we be taking up the strategy? So firstly, we will be seeing the economic distribution of the load, that is the power output of the plant units within a plant. And then we'll see that this strategy what we adopt here is also applicable to any plant system where we neglect the transmission losses are not considered. And then next we will see how the transmission laws in a system also could be adopted into the economic scheduling, for which we have to see that the transmission laws will be expressed as a function of output of various plants, that is the plant generation. Next, after which we have to see how the plant generation, the output of power of the plant can be scheduled, and with the main intention that the total cost of generation comes down. So that and simultaneously we will be able to meet up the system load. Next we'll be moving to what is input-output relationship, the input-output curve of the generating unit. So of course we know that the power plants, when it is, we have got many different generating units within a plant. So for example, I could say if it is in case of Murumatam power plant. So there we have got 6 units, each working out, we have got 130 megawatt of generation, and so totally 6, so total installed capacity comes around 780 megawatts. Maybe in another station like Pannivasal, where we have got 6 units, but there we have got 3 units with 5 megawatt capacity, and we have got another 3 units with 7.5 megawatts capacity, totally coming around 37.5 megawatt capacity. So within a generating plant itself, we find that there are different generating units within a plant. So that's what is the system nature. So we know that many cost is being, huge investment is being done on your power plants, be it your hydro power stations, thermal power stations, or whatever be the power stations, whatever be the type of the power stations. And we see that mostly there will be some initial capital investment done on the power plant, and the other thing is your operating cost or the running cost of the plant. And we see that usually the fuel cost, the staff salary, and the depreciation charges and the maintenance cost, this forms the major part of the operating cost. And we find that in among this, the fuel cost is the major portion of the operating cost that has to be properly controlled, because that exactly determines what should be the power output of that generating station. So if you are able to control the fuel input, we will be able to control the power output of the generator, and we are able to have a control over the economic scheduling. So here onwards, the main importance is given on how to control the fuel cost alone. Has to be, that is what is being taken into consideration. So next is we'll be seeing what is input-output curve of generating unit. So we have to see if we want to vary the power output of a generator, we have to vary what is the fuel input that is being given to that particular generator. And how this fuel input is measured. So usually the fuel input is measured in terms of this much tons per hour or this much MBTU per hour, million British thermal units per hour. So it is either given as how the fuel input is given is either in terms of MBTU per hour or tons per hour. And how we go for your cost. So normally the cost is given as this much rupees per MBTU. So the product of MBTU per hour into rupees per MBTU. So MBTU cancels, so it will be rupees per hour. So finally, the fuel cost will be given either in terms of rupees per hour. So the final calculation will be either, so the product of rupees per MBTU into MBTU per hour. So millions MBTU will get cancelled, so finally it will be rupees per hour. Okay, so the fuel cost will be given in terms of how much rupees is being spent per hour. So that is how the fuel input is taken. It is rupees per hour. So let me suppose that CI is your notation used for representing the cost of the ith plant. So CI, this much cost is being spent for the ith plant. So this much rupees per hour. That is the input cost, that is to generate power PI in the unit I. Okay, so in a plant I have got ith unit that generates PI and the cost corresponding is CI, that much rupees per hour. So let me show you a typical input-output curve. This will be the typical input-output curve of the generator. So in your x-axis we have got what is the power that is generated in megawatts, and in y-axis we have got the rupees in cost in rupees per hour. And something, it's a quadratic relationship. It's a non-linear relationship between these two parameters. And we have to see that there is one inequality constraint is also included in this. So you have to see in a plant there will be a restriction on what should be the real power that is generated and what is the minimum real power that could be generated and what is the maximum real power that could be generated. So that is what is your real power minimum and this is your real power maximum. So the generation in a plant should follow this curve with this inequality constraint. Restriction. You cannot go for a generation lesser than P minimum or you cannot go for a generation more than P maximum. So that is how the input-output curve of a generating unit will be. Now, so this relation what we have seen, this input curve, it will be, this input-output relation is a quadratic relation. So based on which we can say the cost equation can be represented as in terms of generation. Cost is represented in terms of generation as alpha PA square plus beta PA plus gamma I. So that much rupees per hour. So you have to see what's the significance of these coefficients. So gamma I is a coefficient which based on the fixed cost of a plant. So maybe it is something like interest and depreciation, salary, wages. So some amount which has been fixed, that coefficient. So it is independent of the power generator. That's this coefficient. And the second coefficient is your beta I. This is mainly this depends on what is the fuel cost. So what is the cost, and of course we know the generation depends upon the fuel. So this is a factor which is dependent on the real power generator. So and this is the major influencing factor in the cost. And the other coefficient is your alpha I, which is dependent on square. The coefficient is based on what is the square of the power generated. So this alpha I is a coefficient which takes up what is the measurement of losses, power loss in the system. So this will be the relationship between the cost and the power that is generated in the IT unit. And so depending upon if I have got different units in a plant, each unit may have different cost curve relationship. And so, as I have said, it has got different power, different plant may have different generating units within the plant. And if suppose the input-output characteristic of the generating units within the plant all has got same relation, that is, all the plant has got same cost relation, identical input-output relation, then how could be the load distributed among them? We go for equal loading. So all the unit has got an identical relationship, so we can always go for an equal loading on that plant. But sometimes it may not happen so. What happens is the different unit within a plant may have different input-output characteristics. So then equal loading, they cannot be all equally loaded. Then what is the strategy to be adopted? So we have to see, that is, so this relation, this indicates the different input-output characteristics. For a particular input cost, the generating of different units will be different. For the same cost, since they have got different input-output relation, for the same cost, we find that different units have different generation. So that is how the difference goes. So now we have to see in such a situation what is the strategy to be adopted. So next we have to see the what is incremental cost curve. So we have to see what is the criteria to be taken for distribution of load among different generating units within a plant. So if suppose as I have said, you have got different units within the plant and each unit has different input-output relation. The cost is different and based on the generation. So if that is the condition, suppose if I want to decrease a generation on a particular plant, and proportionally I will try to increase the generation on another unit. So one unit I am trying to decrease the generation and another unit I am trying to increase the generation by same amount. Okay, then we have to see the total cost, how it is there. Okay, the total cost, whether it is decreasing or it is increasing. That decides the criteria of distribution of load among that unit. So if I have got two different units, it has got one, I will reduce the generation and I will try to shift that generation to the other plant or the other unit. So if by doing this, the total cost, whether it is decreasing or whether it is increasing, that only will decide how I have to distribute the load among these two units. Okay, so for which we have to know what is called as what will be the change in the input cost for a small change in the input power. So if I want to change what is the power in the ith unit, and we will see what is the corresponding change in the ith unit. So accordingly, we can see that we have to calculate this incremental cost, which is nothing but dCi by dPa. So what will be the change in cost in the ith unit when there is a corresponding change in the power in the ith unit? Okay, so that is nothing but the change in cost by change in power. So we have the incremental cost, the incremental change in generation. Correspondingly, what is the incremental change in cost? That is nothing but the change in real power corresponding to the and corresponding change in the cost. So dCi by dPa is equal to delta Ci by delta Pa. Now of course from this we have got this delta Ci can be represented as dCi by dPa into delta Pi. And so the incremental cost curve is nothing but delta. We have so that we can find out what is the change in the cost. So this is very important. So for an optimal scheduling, we are mainly concerned with this factor, what is dCi by dPa, and this is called as the incremental cost, and it is mainly determined from what is the slope of the input-output curve. Based on that, the relation between your slope. So slope is in your y-axis, we have got your cost, and your x-axis, we have got your input power. So the slope decides what is this change in cost for to a change in power. So that is what is defined as incremental cost, which is dCi by dPi. Now let us say that we have to see what is the incremental cost curve. So incremental cost curve is nothing but a plot which is plotted between your DCI by DPI versus your PI. And so what should be the dimension? So we have to see your cost is always given as rupees per hour and power is given in terms of megawatt. So the dimension of DCI by DPI will be rupees per megawatt hour. So because we have got cost is rupees per hour and P is nothing but megawatt. So the unit of the dimension of DCI by DPI will be nothing but rupees per megawatt hour. And we have to see, so generally the input-output relation is the cost equation is defined by the equation CA is equal to alpha pi square beta pi plus gamma I, this much rupees per hour. And incremental cost, that is nothing but DCI by DPI. So if I differentiate this equation, you will have 2 times alpha I pi plus beta I. So the incremental cost equation is given as DCI by DPI is equal to, for this particular equation is given as 2 alpha I pi plus beta I. So where alpha, beta, gamma are all your coefficients. So this is a typical incremental cost curve. So incremental cost curve is we have got incremental cost which is in rupees per megawatt hour and it is expressed in the y-axis we have got incremental cost and in the x-axis we have got the real power in megawatts. Of course the relationship, approximate accurate relationship is what is shown here, actual relationship, and the dashed line shows the linear approximation of this. So we can see for an appreciable range almost it is linear. It is linear. So we have a linear relationship between these two parameters in an approximate range. So next, moving on to the economic division of plant load between the different generating units in a plant. So let me suppose that we have got in a plant 2 different units. 2 different units has got 2 different incremental cost curve. So accordingly, let this be the incremental cost curve of the first plant and this represents the incremental cost curve of the second plant. So we find that at one point, this plant has got a higher incremental cost when compared to the second plant. So what strategy we adopt for distribution of load among these 2 units? So usually what we try to do is our intention or our objective is to reduce the total cost. So a plant with higher incremental cost will be loaded less and that much loading is increased on this plant. So normally since this plant has got higher incremental cost, you decrease the loading on this unit and that same amount you try to increase on this unit 1. So we can find same thing is said. So when you have incremental cost of this plant is more than the incremental cost of this, and we can see we try to decrease the power output of the unit 2 by delta P, and that delta P I try to increase on the other unit 1. Okay, so this product is delta IC2 into delta P. This will be definitely greater than this. Okay, so in this case what happens? When we see the cost wise, so there will be more decrease in cost rather than, so when here here there will be decrease in cost, correspondingly here there will be an increase in cost, but we find that there will be more decrease in cost when compared to the less increase in cost. Okay, so we can find out the total cost will come down. Okay, so this strategy is what is adopted. So when we have 2 such units in a plant, we try to initially load this unit 2, then lesser load this unit 2, and we try to more load your unit 1. Okay, and then so this change will be continued. We try to proceed till we get that both the incremental cost curve of both the plants will be the same. So till this both will be the same, we try to do. So this will come down, and so we can find that at one particular point of time when I am going on loading this plant, this cost will remain. So this will also try to reach this point. So at one point we can find both the incremental cost will come down. Okay, and then we'll find that the total cost will be minimum. So same strategy also could be extended for a plant which has got more number of units. So in a plant which has got more number of units, there may be a case where if I have got two different plants, two units, one has got the highest cost, the other one has got the low. So usually what we try to do, we decrease the power output of the unit that has got higher incremental cost, and then we increase the power output of the unit which has got a lower incremental cost. Okay, so that strategy is adopted. So by doing so, at one stage we will reach a case where both the units will have the same incremental cost. Okay, so at that time we will find that the total cost of generation will be minimum, and so the general strategy adopted for your economic division of load among the different units within a plant is that all the units must finally operate at the same incremental cost. So that is the strategy adopted. All the units has to be operating with the same incremental cost. So this logic, let's see how it works out mathematically. So let me consider that I have got n number of generating units within a plant, and let the incremental the cost curve, okay, so the input output curve of the units are denoted. Okay, so we have, this is the input, fuel input, so the corresponding cost, this is the power output of that unit. So I am representing, you have a cost which is represented as a function of the power generated in that unit. Similarly, I have got the cost of second unit which is expressed as the generation in that second unit. Similarly, I have got n number of units which is the C and P. So the cost of the nth unit based on the power generated in the nth unit. So what is our problem? We have to distribute a load demand. Okay, it has to be distributed among a set of units, and our intention is to minimize the cost. Okay, so in this case, so what will be the total cost? Total cost is nothing but the cost of individual units. So it is your C1 plus C1 of P1 plus C2 of P2 till Cn of Pn. That total cost is what is your Ct. So our problem, minimization problem, could be stated as to minimize your total cost, but it is being subjected to certain constraints. We have to see what are the constraints in the system. So the constraints is, we have to see that I am neglecting the loss. So I have to see that the total demand will be equal to the total generation. So total demand will be equal to the total generation. So PD is your total demand and this is your total generation. So the difference is nothing but zero. So your demand should match with your total generation. And this is an equality constraint on the system. And we have got another inequality constraint in the system. The inequality constraint is, as I told earlier, there will be restriction on what is the minimum power that could be generated as well as the maximum power. So the power that is generated in the ith unit should be greater than or equal to PA minimum, and it must be lesser than or equal to PA maximum, where I can vary, can take any unit. So it can be I is 1 to n, any unit. So this is our optimization problem. So initially let us not first consider the inequality constraint. So how could the problem be solved? So the problem could be taken as to minimize the total cost subjected to this equality constraint of total demand meeting with the total generation. So this is how we first initially consider the problem as. So we are not currently taking into account the inequality constraint. So mainly we have taken, this is our objective, to minimize your total cost, and with the equality constraint the demand should match with your generation. And we have to see, this is an optimization problem with an equality constraint, and of course we try to use your Lagrangian multiplier method. So we have to see in the Lagrangian multiplier how to define a Lagrangian function. So this Lagrangian function can be formed by augmenting the equality constraint with that of to the objective function using a proper Lagrangian multiplier. So we for this we have to see how the Lagrangian function is defined. Lagrangian function is defined, it is in terms of all your n plant generation, P1, P2 till Pn, and this lambda, it stands for your Lagrangian multiplier, and the Lagrangian function is defined as lambda Lagrangian multiplier times this equality constraint, and that is augmented with your objective function. So this is your objective function plus lambda times your equality constraint. This is the Lagrangian function. So as I have said, lambda is your Lagrangian multiplier, and our intention is this Lagrangian function has to be minimized, and of course with no constraints on it. So we have to see what is the necessary condition for this to be minimum. So what is the, because it's an optimization problem, we have to see what is the necessary condition for minimum. Okay, so for mathematically we know that we have to differentiate that Lagrangian function with respect to the variable p, and that has to be equated to 0. So we have to take dou L by dou p, and pa. So since it is for all your I units, I can take any value from 1 to n. So we have to find, and also we have to find out what is dou L by dou lambda. So we have got all your n variables p1 to pi as well as lambda. So let me consider that if I have got a 3 unit. Okay, so 3 units. So what is your Lagrangian? It is your p1, p2, p3 and lambda. So and what is your the first one is nothing but your objective function. The objective function is sum of all your total costs. So c1 of p1, c2 of p2 plus c3 of p3 plus lambda times your constraint, equality constraint, which is the demand must be matching with your generation, PD minus this. Okay, this is your total generation, this is your total demand. That difference must be 0. So this is the equality constraint. So lambda times this equality constraint plus the total cost. So this is what. Now let me go for your partial differentiation. So we dou L by dou P1. So this will be, when I do this differentiation, so this all will be constant, so it becomes 0. So it's dou C1 by dou P1, and from this is a constant, so you will have minus 1. All the other parameters will be variables, since they are not considered. We have this minus 1. This is dou C1 by dou P1 plus lambda times minus 1 equal to 0. And similarly, we differentiate this dou L with respect to dou P2. So we will have same equation, dou C2 by dou P2 plus lambda times minus 1. So dou L by dou P3 is dou C3 by dou P3 plus lambda. So we are differentiating this Lagrangian function with respect to P1, P2 and P3. And differentiate the same Lagrangian function with respect to lambda also. So when I do it with respect to lambda, this all this entire equation, when it is differentiated, I will have lambda. So lambda 1. So when I am differentiating with respect, the whole term will come. So we have PD minus P1 minus P2 minus P3 equal to 0. So this is for a 3 unit system. So we will have all these 3 conditions. All will be the same. So now let me see, go for a condition where we consider generally n units. So here it is your 3 units where we have to consider your n units. So generalizing, we have general equations dou Ci by dou Pi minus lambda. So we can get, because you see dou C1 by dou P1. So here all is minus number. So dou C1 by dou P1, dou C2 by dou P2. So when I am generalizing it, this equation becomes dou Ci by dou Pi minus lambda equal to 0, where I can take any value between 1 to n. And the final equation is, we have from this equation, PD will be equal to P1 plus P2 plus P3. So here, since it is 3 units, this is sum of this 3 generation, and if it is your n number of units, all n generation. So PD minus sigma I is equal to 1 to n PD. So we have, this is your necessary condition. These 2 conditions has to be met for economical division of the plant load among all your different units. So we have to see this dou Ci by dou Pi is nothing but the change in the production cost of the ith unit for a small change in the ith unit generation. So now, since we know that if the ith unit generation will depend upon that, the production cost of that unit will depend upon that generation alone. So dou Ci by dou Pi can be taken as dCi by dPi, because this ith unit cost depends upon the ith unit generation alone. So dou Ci by dou Pi can be taken as dCi by dPi. So this condition will change to dCi by dPi equal to lambda, where I can take any value between 1 to n. And So we have the solution is the main objective was to minimize the total cost function subjected to this equality constraint, and finally the condition to be satisfied is we have to have dCA by dPA, that is all the plants should have the same incremental cost, and this is your power balance equation. So here totally I have got n number of variables. What are the n number of variables? P1, P2, P3 till Pn. Okay, if n units are there, P1 to P3 till Pn are your n units plus lambda is your one variable. So totally we have got n plus 1 number of variables, and here I have got n plus 1 number of equation. This is n number of equation. dC1 by dP1 equal to lambda, dC2 by dP2 equal to lambda. Like this, I have got n number of equations here, and this is n plus 1 equation. So totally we have got n plus 1 variables and n plus 1 equations. Okay, so from this equation we can say that the main criteria to be followed is equal lambda, that is you have equal incremental cost. So this rule is called as your equal incremental cost rule, and this equation is called as your power balance equation. This is what has to be maintained. So but still one condition is we have not considered the inequality constraint. We have considered only with the equality constraint, we have not considered with the inequality constraint. What is the inequality constraint? That is the real power generator has to be within your limits. Okay, so but if suppose as per the previous solution, if you are able to get the generation of the plants, and if the generation comes within the limits, then of course this condition is also satisfied. This condition is satisfied, so we have an optimum solution. But in case if a particular unit within a plant, the limit is violated, that is if the generation goes lesser than the minimum or if it goes greater than the maximum, in that case what we have to do is fix up the generation of the ith unit either at the minimum value or at the maximum. Okay, if it is lesser than minimum, you put it at minimum limit. If it is greater than the maximum, you put it at the maximum limit. Once that unit generation is fixed, then the remaining load has to be distributed among the remaining units. Okay, one unit is fixed based on this limit variation. The remaining load has to be distributed among the remaining units of the plant with the same criteria, that is equal incremental cost. So we'll fix up the generation of that plant which is violating the limit while the load is distributed among all the other plants. And so the next session we will be seeing the problems with respect to this concept of economic load dispatch. Thank you.